Hi, so basically my name is Ramu and this is our group presentation. So it starts off with time domain analysis. So basically, what is time domain analysis? Time domain analysis observes how signal amplitudes vary with time. So basically you can see the amplitude in the y-axis and the time in the x-axis. So we see that in this graph we can see it appears very thick. Okay, as we can see, it appears very thick and then it looks disoriented. So in this we can say that the presence of continuous additive noise, okay, the presence of noise is more, okay, it is more than transient noise actually. So there is no clean fluctuation, okay, there is no clean fluctuations in this graph. So this indicates that the frequency is kind of high and at the same time there is noise present. So the noise is non-transient, okay, so it exists from the start, as you can see over there, until the end. All right, so it is additive, okay, because it is directed to the original signal. So this is how the noise is present over there. So what is the effect on signal amplitude and quantization? So you see that the frequency interference occupies a large portion of the amplitude range. So what we can understand is that this pushes the signal closer to the quantization limit. So this increases the risk of actually, uh, you know, overlapping with each other. So the large amplitude sinusoidal noise pushes the signal closer to quantization limits. So this restricts the headroom for the original audio. So basically we cannot hear the audio from this. So that is my part for time domain analysis, and we will move on to the next part. Thank you.
Hi, I'm Sneha. I'm going to explain about spectrum analysis. This slide shows the frequency spectrum analysis of an audio signal using MATLAB. The audio files audio 09 is first loaded and sampling frequency is obtained. The fast Fourier transform or FTDT is the applied to convert the signal from the time domain into the frequency domain. A frequency factor is the created based on the sampling and the FTT mechanism normalized to mean correct amplitude scaling. Only the signal side spectrum is plotted since it represents the physical meaningful positive frequency. The spectrum allowed us to clearly identify the dominant frequency component present in the original audio signal. These figures show the signal side amplitude spectrum of the original audio signal. This x-axis represents frequency in Hertz, while the y-axis shows the normalized amplitude. We can observe a strong peak at low frequency, indication that most of the signal energy is concentrated in this region. As the frequency increases, the amplitude gradually decreases. Meanwhile, higher frequency components contribute less to the overall signal. This spectrum helps us identify the dominant frequency range and understand the frequency context of the audio signal.
Assalamualaikum. My name is Muhammad Shakir bin Muhammad Noor. Matrix number B122310646 from BERG, and I will be explaining about calculation for uncontrolled and control rectifier. So for the uncontrolled rectifier, first we calculate for the RMS output voltage and current. Also for the ideal value, V out RMS equal to Vm over square root 2 equal to 169.71 over square root 2 equal to 120 volt. So for Is RMS equal to I not RMS equal to Vm over R equal to 169.71 over 20 ohm equal to 6 ampere. So for the practical, it is the simulation value. V not RMS equal to 168.31 over square root 2 equal to 119 volt, while for the I not RMS equal to 119 volt over 20 ohm equal to 5.95 ampere. So the second one, we calculate for the peak output voltage and current. Ideal value for V dot peak which is equal to Vm equal to 120 Vrms times square root 2 equal to 169.71 volt. For the I naught peak, which is equal to V naught peak over R equal to 169.71 volt over 20 ohm equal to 8.49 ampere. So for the practical value, simulation value, so V naught peak equal to 169.71 minus 1.4 volt equal to 168.31 volt. This is because the silicon diode drop of 0.7 volt per diode, so is 2 diode times 0.7 equal to 1.4 volt. So for the I naught peak equal to 168.31 volt over 20 ohm equal to 8.42 42 ampere. Sorry. And the last one, we calculate the power factor, which is equal to 1.0. It is unity because since the load is purely resistive, which is 20 ohm, and the circuit is uncontrolled, the current drawn from the source is a pure sine wave that is exactly in phase with the voltage. There are no phase shift and no significant harmonic distortion in the source current. So we continue for the calculation for control. First one, we calculate the RMS output voltage and current. So the V no RMS equal to Vs RMS times square root 1 minus alpha over pi plus sine 2 alpha over 2 pi. So the alpha given is 60 degree. So we change from degree to radian, which is 60 over 180 times pi equal to 1.047 radian. So we insert the value 120 times square root 1 minus 1047 over pi plus sine 2 alpha over 2 pi equal to 107.6 volt. So for the I know RMS is equal to V naught RMS over R equal to 107.6 volt over 20 ohm equal to 5.38 ampere. So the second one, we calculate the peak output voltage and current, the same with the uncontrolled one. So the V ideal value, the V naught peak equal to Vm is equal to 120 Vrms times square root 2 equal to 169.71 volt. The I naught peak is equal to V naught peak over R, 169.71 over 20 equal to 8.49 ampere. The practical simulation value, V naught peak equal to 169.71 volt minus 1.4 volt equal to 168.31 volt. So for the power factor is equal to V naught RMS over Vs RMS. The V naught RMS value is 107.61, 1.1067.6 actually over 120 volt and is equal to 0.90, which is lagging because the delay in the firing distort the current waveform even though the load is purely resistive.
So for comparison between these two filters, which is FIR and IIR, we're gonna play the original audio first.
Tell someone to love me. I need to rest in arms.
So as you can listen, the frequency of 240 Hz, which is spike over here, destroying the original song. So we apply FIR and IIR to eliminate the spike, which is on 240 Hz. So after FIR, our spike become lower, which is half of the original spike, which is around 0.23 or 0.24, and then it become 0.14 or 13. So this is the audio after we apply FIR filter.
Tell someone to love me. I need to rest in arms.
So the constant sound is still there, but maybe not too noticeably slow. So but the graph show that the spike is lowered to half. So we apply IRR filter, which as you can see completely destroyed the constant sound, constant spike, which is around 240, and it goes lower to maybe to the original song. So the graph is scaled to micro, so the magnitude over here. So this is after the IRR filter.
Tell someone to love me. I need to rest in arms.
So as you can hear, the constant sound of 240 Hz frequency is no longer there, and the audio become clean and filtered.